You know, inside every single piece of metal, every weld holding our world together, there's a hidden landscape. Most of the time, it's totally solid. But sometimes, lurking deep inside, are tiny, invisible flaws, weaknesses that can lead to absolute disaster. Today, we're going on an invisible hunt, using some incredible technology that lets us, well, see with sound. You know, inside every single piece of metal, every weld holding our world together, there's a hidden landscape. Most of the time, it's totally solid. But sometimes, lurking deep inside, are tiny, invisible flaws, weaknesses that can lead to absolute disaster. Today, we're going on an invisible hunt, using some incredible technology that lets us, well, see with sound.
I mean, that's the core of it, isn't it? When a crack is buried deep inside a steel pipe, or a critical part of a power plant, you can't just cross your fingers and hope for the best. Figuring this out has been one of engineering's most important safety missions for a long, long time.
And the stakes here, they could not be higher. We're not talking about small cosmetic stuff. We're talking about the safety of our most critical infrastructure. Just one single undetected crack in a pipeline or an airplane wing, it can grow under stress until the whole thing fails. And that can be catastrophic. So finding these flaws isn't just a cool engineering puzzle. It's all about keeping people safe.
So if you can't use your eyes, what's left? The answer is sound, but not just any sound. We're talking about incredibly high-frequency sound waves, way, way beyond what any human can hear. This is the world of ultrasonic testing.
The whole concept is basically sonar for solid objects. You know, just like a submarine pings the ocean floor or a medical ultrasound lets you see inside the human body, this technique, called ultrasonic testing, or UT for short, sends a pulse of sound into a material and then just listens for the echo. And the best part? It's completely non-destructive. You can inspect a critical part without leaving so much as a scratch.
Okay, so here's how it works in its simplest form. You have a probe that sends a quick pulse of sound into the material. That sound travels in a straight line until it hits something. Now, if the material is perfect, the sound just travels all the way to the back wall and bounces right back. But if there's a flaw in there, a crack, an air bubble, whatever, it creates an echo that comes back much, much sooner. By measuring the exact timing of those echoes, an operator can literally map out the unseen world inside that piece of steel.
Now, while that basic idea is pretty straightforward, the technology has gotten incredibly sophisticated. So today, we're going to meet two of the real heavy hitters in this field, TOFD and POT.
The best way to think about these two is like specialists on the same elite team. TOFD, that stands for time of flight diffraction, is the master of sizing. It is incredibly precise at measuring a flaw down to the millimeter. Then you have POT, or phased array ultrasonic testing. POT is the master of finding. Think of it like a super high-tech searchlight that can sweep through the material to hunt down any potential problems. They really are a dynamic duo.
And you can see their totally different strategies right here. On the left, you've got TOFD, our sizing specialist. It uses this fixed pitch and catch setup with two separate probes. It's built for extreme precision in one area. But then look at POUT, the finding specialist. Its probe is basically a whole row of tiny transmitters that can be fired in a specific sequence. This lets the operator steer the sound beam electronically, sweeping it through the metal like a searchlight, without even moving the probe. That versatility is what makes it so good at hunting for flaws.
Let's zoom in on TFD's real superpower, its sense of timing. See, when its sound wave hits a crack, it doesn't just get one big echo back. It gets two tiny, faint, separate signals. One diffracted from the very top tip of the crack,
and another from the very bottom tip. By measuring the microscopic delay in time between when those two signals get back, the system can calculate the height of that flaw with just incredible accuracy.
So the machine sends out sound. It gets these echoes back. But what does that actually look like for the technician? Well, the result is a digital image, kind of like a grayscale map of what's inside. And just like a radiologist reading an X-ray, these technicians learn to read the unique language of these images.
This is what they see on the screen. For instance, porosity, which is really just tiny trapped gas bubbles from the welding process, it looks like a scattering of small individual dots. Slag, on the other hand, which is an impurity that got stuck in the weld, well, that creates a completely different visual signature. A trained eye can look at this screen and instantly know what kind of problem they're dealing with. Now take a look at this phased array scan. That sharp, bright line, that is the unmistakable signature of a crack that's breaking the surface. So think about it. The sound is supposed to travel down and bounce off the back wall in a nice V shape. But here, that crack acts like a mirror, bouncing the sound back way too early. It creates what they call a half V path. And to a technician, that's a dead giveaway that they're looking at a very serious problem.
Of course, real-world inspections are almost never that simple. A single scan can tell a whole complex story. Right here, we can see signs of incomplete fusion. That's where the weld didn't bond right to the side, and it's right next to some slag. A skilled analyst doesn't just see a couple of flaws. They see the story of how this weld was made, and they can pinpoint exactly where things went wrong.
Okay, we've talked a lot about some amazing technology, but here's the thing. The most advanced, most expensive machine in the world is completely useless without a skilled human being running it. In fact, you could argue the human element is the single most critical part of this whole process. Because really, it's not the technology that finds the flaws. It's the person using the technology. Every single setting, the type of probe, the angle of the beam, the sensitivity, all of it has to be perfectly calibrated for that specific inspection. If you get any part of that setup wrong, your multi-million-dollar machine is just going to produce a screen full of garbage. Let me show you exactly what I mean. On the left, you see a good, clean scan. Now watch what happens if the operator makes just one little mistake. If they set the gain, which is basically just the volume control for the echoes, too high, you get this on the right. It's the exact same piece of metal, but the image is flooded with electronic noise. A massive, dangerous flaw could be completely hidden in all that static just because of one wrong setting.
And it's not just the volume. The timing has to be perfect too. The operator sets up what's called the gate, which is the little window of time that the machine is actively listening for those returning echoes. If they set that gate to close too early, like you see here, the machine never even hears the echo from the back wall. Any flaw in the second half of the material is now totally invisible. It's such a tiny adjustment, but it makes the difference between seeing a crack and missing it completely.
This is exactly why the source material really hammers this point home. It says that because there are so many variations between flaws and setups, evaluator experience and analysis skills are very important as well. The technology gives you the data, but it's the experienced human who has to turn that data into a real decision about whether something is safe or not. All right, so let's wrap all this up. What are the big things to take away? First, ultrasonic testing gives us a kind of superpower, the ability to find dangerous flaws that are totally hidden from view. Second, remember our specialists. TOFD is the master of sizing, and POUT is the master of finding. Third, these scans aren't just random noise. They're a visual language that, if you know how to read it, tells you everything about the health of a material. And finally, and this might be the most important one, never, ever forget that the skilled operator is just as crucial, maybe even more so, than the amazing technology they're using. You know, using sound to see inside solid steel, that's just one application of this kind of thinking. It really makes you wonder, what other invisible worlds are we just beginning to explore? From mapping the connections in the human brain to searching for resources deep inside the Earth, we're constantly finding new ways to see the unseen. What do you think the next big frontier will be?